So this is actually a talk by Dan Dragos Stefanescu, and he's our partner at Sanofi, and I guess it was, he works in Germany near Frankfurt, in scientific computing group at Sanofi. So he asked me to come and help give his talk for him. So yeah, what Sanofi was trying to do is a new approach to similarity graph, to do investigation. And, I apologize. So the talk is called Novel Similarity Graphs, and it's using Neo4j as the graph database, ChemAxon and ChemAxon components, and then Tom Sawyer perspectives for data integration and graph and data visualization, as well as we help with the infrastructure for the whole, to provide an integrated application instead of going in and out of different tools. So the end result is a single integrated application with a single experience. So this is the talk is going to be half the talk is going to be this PowerPoint, and in the second half we have a video that was recorded by Dragos. We call him Dragos. Where he gives a voiceover video of the application, and because I'm not a chemist and he is. So So first they were trying to identify the needs that they had, they really wanted to do. Sanofi really wanted to do efficient exploration of the chemical space around biologically active chemical matter, and they wanted integration of the diverse information linked to the compounds that they have, activity, related drugs, commercially available compounds, etc. And then they wanted efficient navigation and traversal and visualization of that data. And a lot of the motivation for a graph database is related to as graph databases are more about nodes and relations, and it's often about friend of a friend, neighborhoods, and exploration around the neighborhoods of certain nodes of interest. So that's what drives the need for the graph database. So you don't have to write these complicated joins and search and write complicated SQL and the like. So it eliminates a lot of that complexity, and the performance is much better. So the idea is to efficiently navigate and visualize these neighborhoods and then exploit the relationships that are around these compounds, I think. So the business needs are like to create interactive and highly visual traversal of this chemical space. And some of the drivers were they needed something that could scale very well. So they needed very, very good performance for very large data sets. And the view at Sanofi was they need more high-end visualization to depict these relationships that they're trying to express and expose to the scientists. And they think, because of this neighborhood kind of work, they can expose information that might have been overlooked in the past, because it wouldn't come out of the queries that they had and the like. So the idea was to have, wanted to have user, friendly applications for the scientists, where like to ask questions like, what are the nearest neighbors of a given compound that contain a scaffold A and show a high permeability? So that's one kind of set of a question. Which compounds show activities on targets A and B and have a reasonable ADME profile? And is there a commercially available compound similar to that compound A that comes with pharmacological data that might be used as a tool compound? So something they could buy off the shelf, for example. The previous work, there are other kinds of data visualization, but the environments, they might have had queries on SQL databases, and then they would wind up exporting into separate tools and the like. And the data, in the past was always in relational databases. And the big issue, I think, was the complexity of doing the research. So like Sanofi explained to us that a single search may have taken minutes, for example. And then if you wanted to do a walkthrough of a set of compounds, you'd have to do a series of successive searches, and then that might take a couple of hours or something. So the idea of query, and then you would do data export, and then external visualization in the past, and then and manual selection. So, but and then a lot of time is wasted in this older or more traditional way of working. So, and then hours go by so we're trying to take that hours down to minutes, or something like this. This is getting over my pay grade at this point, but so in building the Similarity tool, their goals were to calculate these FP4 fingerprint and Tanimoto similarities. So they have for 10 neighbors, this canonical smiles, Inchi keys, and structure pictures for all Sanofi screening collection compounds. So they wanted to use the new. They wanted to avoid having to go into Oracle and the graph database. They wanted to avoid duplication of the data across different silos. So that's why they began to work with ChemAxon so they wanted to remove the Oracle dependency that they had in the past. So they used the new ChemAxon. It might have been renamed, but ChemAxon for Neo4j plugin for substructure and similarity searches. And that's the idea of that is to help get rid of the Oracle dependency, avoid the duplication. And then they want compound annotations to do physical PChem work. So solubility mean, log D, HPLC mean, and other calculated properties, and then E, ADMA. So PT max mean, metabolism, human mean, metabolism rat mean, and then also connecting it up with related Sanofi project names in their own taxonomy or whatever. They have their own naming system. Sorry. Oh. Is it? Uh-oh. Sorry? Oh, okay. Uh-oh. Technical difficulty. Sorry. Oh, there it is. Did I go? I think that's. I hope I went one slide. Let's see. Yeah. Okay. So they were saying what are the steps that they wanted to do to build this new. They call it the Similarity Graph tool. They wanted to load the data into Neo4j database, graph database. They wanted to use our Tom Sawyer perspectives to build a complex web application and have a web application for their users. And we were supposedly selected because of the data integration I mentioned before, the capability and data integration that we have. And then we were probably the first American graph visualization company. So we work really long time in graph technology architects. So they chose us for these reasons. And then they really work with ChemAxon Marvin JS Sketcher for drawing structures for substructure search. And that's all web components. So it's kind of a very modern, nice web environment for the end users. Okay, see if I can. There we go. So there's some features. They want to retrieve the nearest neighbors of a molecule. They want to highlight highest, second highest, and chemically similarity edges of a molecule node for interactive graph traversal. They want to allow scientists to track the path and order of visited compounds. They want to export as well and do tool integration with other things that are downstream. So they export selected compound IDs for further analysis. And he mentioned, I know there's several tools that were mentioned, but for example, this Certara D360. And we have like a very advanced filtering architecture to filter data in different ways. So filtering on edge and node properties, and we do a lot of data-driven graphics. So coloring and coding rules applied to the graphics. So let's see if I can. Okay. So they want to find the shortest path between two molecules, but respecting the biological context. So consider visible nodes of the currently displayed graph, or they'll want to go and do it against a database query. They want to enrich nodes. So not only do they have the Neo4j, they also import data in from CSV files for other reasons I don't fully understand, but they do export and unify the model, linking by compound ID. They display scaffolds and show compounds with similar SAR. They're trying to say, yeah, same biological function but low chemical similarity, which and then the data, the video we're going to show is obviously with the public domain ChemBL data set, so from European Bioinformatics. So this demo was against about 2 million compounds. The demo we're about to show. So I think. Okay, yeah. So yeah, ChemAxon, Tom Sawyer Software, Neo4j, and Sanofi. Different Sanofi scientists participated in the project, and it's still ongoing. This application we're going to show, this video, was about 15 months of work. Not full time all the time, but about 15 months of work. It was done by one of our senior solutions architects working with Sanofi's at their Sanofi's direction. So we built it for them, and but they were the advice like what to do. We didn't know ourselves what to build, but that's what the video will show.
Hello, my name is Dragos Stefanescu, and I'd like to thank ChemAxon for the invitation to their user group meeting 2019. I'm a medical computer scientist working for Sanofi Scientific Computing Department in Germany, which is part of research, and it's my pleasure to guide you through this video demonstration of our Similarity Graph tool. Please note that all examples shown in this video are based on publicly available ChemBL data and for illustration purpose only. This web application was built using Tom Sawyer perspectives, which will be subsequently abbreviated as TSP. Let's get started. First, we do a simple structure search of a ChemBL compound. We are using here Marvin.js from ChemAxon to draw load structures. Our TSP web application sends them to our Neo4j graph database for performing substructure searches, utilizing the ChemAxon for Neo4j plugin. As a result of this search, we get a Starlike Graph where the searched compound node is located at the center. Its nearest neighbors in terms of chemical similarities are placed around this center compound node and connected via similarity edges to it. The chemical similarity value is labeled on the respective edge. Clicking on a node displays two things. First, the edge with the highest similarity gets automatically highlighted in red. Second, the property inspector on the left shows all properties of the selected object. In this case, we have the ChemBL ID 1834852. We have a calculated molecular weight, calculated A-log P, calculated formal charge, and many others, as well as a ChemBL URL. Let's click on that. As you can see, the respective ChemBL page has opened for this compound. Let's go back. We would like to display all structures for the compounds on the screen. Here they are. Let's apply two filters that I pre-configured. An A-log P filter that keeps all that are less or equals than 4.334, which is actually the A-log P of the center compound, and another filter that keeps less or equals to a molecular weight of 517. After applying it, you see that the respective nodes and edges got filtered out. Now let's traverse the path along its highest similarity edges. Start with the center node, double-click on it, and that gives it its order number 1 because it's the first node of the path we want to traverse. The higher similarity edge is this. Double click on that. And now we got the next one marked on our path. Let's keep the filter going. And also traverse this edge now. So you can see there are two edges having the same similarity value. And apply the filter also here. Let's do an auto layout to make it a little bit nicer. And we can also toggle between the full graph and just our path. Let's switch the layout to circular, which naturally shows the chemical similarity clusters that we have in our database. Now we like to calculate the shortest path between, let's say, this compound and this one here. And we do that for the visible compounds on the screen. Again, we can also toggle between the non-shortest path and the rest of our graph back and forth. We remove the shortest path for now as we don't need it at the moment. Of course, we can also zoom in and out, move around everything, have a look at the nodes, click each one we like. Let's go back to our start node and let us display all the related projects. Let's do an auto layout and maybe switch back to the non-structures. As you can see, we may now need a different way of layouting, and we choose hierarchical layout for that. That looks much nicer. Next, we would also like to display all the scaffolds for that compound. And you can see them here and see which scaffold is shared by which compound on the screen. Again, we can zoom in and out and look at the interesting areas of our graph. As we are currently only interested in hERG-related compounds, we're going to remove this other project here. And do an auto layout. In the next step, we like to enrich our graph with some data that we have in a CSV file. It's hERG activity data. And we specify the file name, the separator, and the decimal delimiter, and join the data from the CSV file by compound ID. So it found actually 3 matching nodes in our screen graph. So let's remove the filters and look at another attractive feature, which is the color coding. So let's see first all nodes that have a hERG activity. And they are colored in yellow. So if we click on one of them, we see that this hERG activity properties shows up for these yellow marked nodes. Okay, now we remove that color coding for it. And let's say we're interested in color coding based on more than one property. So I've prepared a color coding rule which says C log A log P should be less than 3.971 and the hERG activity should be less than 8.06. Let's apply that and see what we get. We can also highlight the first compound that we searched for at the beginning. For that I have prepared this color coding rule, and you see it's the one here. So we now zoom into the graph and think that this could be interesting to look at these nodes, because the ones colored in green fulfill our search criteria for color coding. At this point in time, it's worth mentioning that we can store our graph and also load it afterwards. We could also send it to another user who opens it on his screen within the application and starts working maybe on the same or different branches of the graph. Let's do that. Okay, so the graph was stored. Now let's pretend we were different users, so I will clean that area here. So we start with an empty graph. It's also worth mentioning that the graph that's currently depicted gets automatically saved after a minute of non-use of the application. So it gets saved to the server, so when you go for meetings or for lunch, it will not disappear. So now we open the graph that we stored, pretending to be another person. And there it is. So the other person can, but is not forced to apply the color coding rules. They are automatically loaded with the graph that was sent, and we can save and load color coding rules that we have and share with others. For the compounds we are now actually interested in, we could mark them pressing the control key and right mouse click and send them to other tools, in-house tools like Certara D360 or other in-house tools, and just continue analyzing these maybe interesting compounds. For now, another interesting option is clustering. Let's say we want to cluster all these compounds that are in our graph and cluster them in exactly 5 clusters. And for the compound weight, we choose the triangles that we calculated. That's a clustering algorithm provided by Neo4j. So we click on apply, and underneath there's a table view, which we can also sort by the cluster number, and we can see that all our compounds have been automatically assigned according to their triangle count to one of the 5 clusters. So we could use that and export it to Excel and use it for further analysis in different tools. So I'm going to remove the scaffolds because we don't need these any longer for the next example. I'm adding a new compound to the already existing graph. And as you can see, these 2 graphs are not connected with each other yet. So let's see if we find the shortest path between these 2 compounds here based on data from the Neo4j database. So we perform load shortest path from database. And let's choose the orthogonal layout for that. And as we can see, there is a shortest path, which we will toggle to so it becomes clearer. Let's do auto layout. And there it is, shortest path from these two compounds is right here. We are now at the end of my video demonstration. In case of any further questions, please do not hesitate to contact me at this email address. Thank you for your attention, and bye-bye.
So you pre-calculate and store the 10 most similar compounds to every compound. But when new compounds roll in, they could be more similar and displace some of those. So do you recalculate that, or do these graphs get out of date really fast as new compounds roll in?
Oh, no, they can calculate it dynamically. So I don't know why he had that 10 rule at the beginning. I think it's all dynamic. I don't believe it's pre-calculation.
I'm sorry.
I have an answer for that. Because I've also contacted with Dragos about that. So currently they are pre-calculating it because they are using some special similarity descriptors, and I guess it is a Tonem automatics, but the descriptors are there. It's not the one which we provide in the Neo4j cartridge. But if you are using the Neo4j cartridge, you can calculate it on the fly. So that's why you are right. If they have something new is coming, they have to calculate it on their data set.
Yeah, I just wanted to say, like, we do graph analysis in our data model, and there's also some graph analysis in Neo4j as well. So there's graph analysis in two different places. Both Neo provides some, and Tom Sawyer provides some, depending.